Hello everyone, welcome to our new topic, the electric potential. In this lesson, we will learn about energy associated with electrical interactions. Every time you turn on a light, listening to your favorite songs in a speaker, or talk on a mobile phone, you are using electrical energy, an indispensable ingredient of our technological society. What causes lightning? Before we will answer that question, we will study first the electric potential and how it explains the occurrence of lightning. In our study of mechanics, we learn the concepts of work and energy. We learned that an object has gravitational potential energy because of its location in a gravitational field. For example, we have a ball moving from point A to point B under the influence of gravity with force equals to its weight, which is mass times gravity. Regardless of the path from A to B, the work done by gravity is the same. The work done by gravity is the difference between the potential energy at point A minus the potential energy at point B, or we can say that it is the negative of the change in potential energy, which is also equal to mass times gravity times height. In this figure, a pair of charged parallel metal plates sets up a uniform downward electric field with magnitude E. The field exerts a downward force with magnitude on a positive test charge. As the charge moves downward a distance d from point A to point B, the force on the test charge is constant and independent of its location. So the work done by the electric field is the product of the force magnitude and the component of displacement in the direction of the force. The electric potential energy in a uniform field is the product of the magnitude of the test charge times the dot product of the electric field and displacement. If the test charge is positive, the potential energy decreases when it moves with the field. The field does positive work on the negative charge. But when the positive test charge moves opposite with the field, the potential energy increases, and field does negative work on the positive charge. Remember, moving the positive charge towards the positive terminal will increase the repulsive force, and it requires external work. Thus, the field does negative work. On the other hand, when a positive charge moves to the negative terminal, the field does positive work. If the test charge is negative, the potential energy increases when it moves with the field. The field does negative work on the negative charge. But when the negative test charge moves opposite with the field, the potential energy decreases, and field does positive work on the negative charge. A test charge Q0 moves along a straight line extending radially from charge Q. As it moves from A to B, the distance varies from RA to RB. The force is not constant during the displacement, and we have to integrate to calculate the work WA to B, done on by this force as moves from A to B. The result is Q times Q0 over 4 pi epsilon naught times 1 over RA minus 1 over RB. The work done by the electric force for this particular path depends only on the endpoints. A more general displacement shown in this figure in which A and B do not lie on the same radial line. The work done on Q0 during this displacement is given by WA to B equals integral of F cosine phi dl from RA to RB. That is, the work done during a small displacement dl depends only on the change dr in the distance r between the charges, which is the radial component of the displacement. The work done on Q0 by the electric field E produced by Q depends only on RA and RB, not on the details of the path. These are the needed characteristics for a conservative force. The electric potential energy of two-point charges Q and Q0 is U equals 1 over 4 pi epsilon naught times Q and Q0 over R. The potential energy U is 0 when Q and Q0 are infinitely far apart. Therefore, U represents the work that would be done on the test charge Q0 by the field of Q if Q0 moved from an initial distance r to infinity. If Q and Q0 have the same sign, the interaction is repulsive. This work is positive, and U is positive at any finite separation. If the charges have opposite signs, the interaction is attractive. The work done is negative, and U is negative. Suppose the electric field in which charge moves is caused by several point charges Q1, Q2, Q3, at distances R1, R2, R3, from Q0 as seen in this figure. For example, Q0 could be a positive ion moving in the presence of other ions. The total electric field at each point is the vector sum of the fields due to the individual charges, and the total work done on Q0 during any displacement is the sum of the contributions from the individual charges. Example problem. 2 point charges are located on the x-axis. Q1 equals negative E at x equals 0, and Q2 equals E at x equals A. Find the work that must be done by an external force to bring a third point charge Q3 equals E from infinity to x equals to A. Find the total potential energy of the system of 3 charges. The work W equals the difference between the potential energy U associated with Q3 when it is at x equals to A, and the potential energy when it is infinitely far away, which is 0. So we have W equals U equals Q3 over 4 pi epsilon naught times Q1 over R13 plus Q2 over R23, where R13 is to A and R23 is A. Then the work done is E over 4 pi epsilon naught times negative E over to A plus E over A equals E squared over 8 pi epsilon naught A. The total potential energy of the 3-charge system is 1 over 4 pi epsilon naught times Q1 Q2 over R12 plus Q1 Q3 over R13 plus Q2 Q3 over R23, where R12 is equal to A, R13 equals to A, R23 is equal to A. The total potential energy is 1 over 4 pi epsilon naught times negative E times E over A plus negative E times E over to A plus E times E over A equals negative E squared over 8 pi epsilon naught A. Electric potential is not the same as electrical potential energy. Electric potential is electrical potential energy per charge. It is denoted by the symbol capital V, which is equal to the electric potential energy U over the charge Q0. An object of greater charge has more electrical potential energy in the field of the charged dome than an object of less charge, but the electric potential of any charge at the same location is the same. The SI unit of measurement for electric potential is the volt, named after the Italian physicist Alessandro Volta. The symbol for volt is V. Potential energy is measured in joules and charge is measured in coulombs. Thus 1 volt is equal to 1 joule per coulomb. We can think of the potential difference between points A and B in either of 2 ways. The work done by the electric force when a unit charge moves from A to B, or the work that must be done to move a unit charge slowly from B to A against the electric force. The potential of A with respect to B is VAB equals VA minus VB. To find the potential V due to a single point charge, we divide the electric potential energy U by Q0, which is equal to 1 over 4 pi epsilon naught times Q over R, where R is the distance from the point charge Q to the point at which the potential is evaluated. If Q is positive, the potential that it produces is positive at all points. If Q is negative, it produces a potential that is negative everywhere. In either case, V is equal to 0 at or equals infinity, an infinite distance from the point charge. For the potential due to a collection of point charge, electric potential V equals 1 over 4 pi epsilon naught times the summation of Qi over Ri for all I. When a particle with charge Q moves from a point where the potential is VB to a point where it is VA, the change in the potential energy U is UA minus UB equals Q times VA minus VB, which is equal to VAB. If the charge Q equals the magnitude E of the electron charge, 1.602, times 10 to the power of negative 19 coulomb, and the potential difference is VAB equals 1 volt, the change in energy is UA minus UB equals 1.602 times 10 to the power of negative 19 coulomb times 1 volt, which is equal to 1.602 times 10 to the power of negative 19 joules. The quantity of energy is defined to be 1 electron volt, which is equal to 1.602 times 10 to the power of negative 19 joules. Potential due to two-point charges sample problem. An electric dipole consists of point charges Q1 equals positive 12 nanocoulombs and Q2, which is equal to negative 12 nanocoulombs, placed 10.0 centimeters apart as seen in the figure. Compute the electric potentials at points A, B, and C. At point A, we have R1 equals 0.060 meters and R2 equals 0.040 meters. So the potential VA is equal to 1 over 4 pi epsilon naught times the summation of Qi over I for all I equals to 1 over 4 pi epsilon naught times Q1 over R1 plus Q2 over R2. This gives us 9 times 10 to the power of 9 Newton meter squared over Coulomb squared times 12 times 10 to the power of negative 9 Coulomb over 0.060 meters plus negative 12 times 10 to the power of negative 9 Coulomb over 0.040 meters. The result is negative 900 volts. At point B, we have R1 equals 0.040 meters and R2 equals 0.14 meters. So VA is equal to 1 over 4 pi epsilon naught times Q1 over R1 plus Q2 over R2. This becomes 9 times 10 to the power of 9 Newton meter squared over Coulomb squared times 12 times 10 to the power of negative 9 Coulomb over 0.040 meters minus 12 times 10 to the power of negative 9 over 14 meters. The result is 1930 volts. At point C, we have the same value for R1 and R2, which is 0.13 meters. The charges have the same value, but opposite sign. Thus, the potential at point C is 0. Moving through a potential difference sample problem. A positive particle moves from point A to point B with the presence of two charges Q1 equals 3.0 nanocoulomb and Q2 equals minus 3.0 nanocoulomb. Calculate the potential difference VAB. To calculate the potential VAB, we must calculate first the potential at point A and potential at point B. At point A, R1 is 0.01 meters and R2 is 0.02 meters. Thus, the potential at point A is 9 times 10 to the 9 Newton meter squared per Coulomb squared times 3 times 10 to the power of minus 9 over 0.01 meters plus minus 3 times 10 to the power of negative 9 Coulomb over 0.02 meters. The result is 1350 volts. At point B, R1 is 0.02 meters and R2 is 0.01 meters. The potential at point B is minus 1350 volts. Finally, the potential difference VAB is VA minus VB equals to 27 volts. A corona discharge is an electrical discharge caused by the ionization of a fluid such as air surrounding a conductor carrying a high voltage. It represents a local region where the air has undergone electrical breakdown and become conductive, allowing charge to continuously leak off the conductor into the air. A corona occurs at locations where the strength of the electric field around a conductor exceeds the dielectric strength of the air. It is often seen as a bluish glow in the air adjacent to pointed metal conductors carrying high voltages, and emits light by the same property as a gas discharge lamp. An equipotential surface is a surface on which the electric potential is the same at every point. If a test charge Q0 is moved from point to point on such a surface, the electric potential energy Q0B remains constant. In a region where an electric field is present, we can construct an equipotential surface through any point. Because potential energy does not change as a test charge moves over an equipotential surface, the electric field can do no work on such a charge. It follows that electric field E must be perpendicular to the surface at every point so that the electric force Q0E is always perpendicular to the displacement of a charge moving on the surface. Field lines and equipotential surfaces are always mutually perpendicular. When all charges are at rest, the surface of a conductor is always an equipotential surface. Since the electric field E is always perpendicular to an equipotential surface, we can prove this statement by proving that when all charges are at rest, the electric field just outside a conductor must be perpendicular to the surface at every point. In particular, at any point just inside the surface, the component of E tangent to the surface is 0. It follows that the tangential component of E is also 0 just outside the surface. It also follows that when all charges are at rest, the entire solid volume of a conductor is at the same potential.
Thank you for watching. I hope you learned something new today.